of Cornell University.
Well, let's go back to this one. All right. So these are simple buffer reactions. They happen normally in soils, okay? But from a management sense, we might in fact want to raise or lower the pH intentionally. To do that, we need to think about this whole issue of the reserve acidity. We need to figure out what we need to know what the total acidity is. We need to know what the pH is of our active soil solution, the active pH, but we also need to know what's going on with the exchangeable as well as that reserve, the residual, okay, or the structural pH. Because I need to be able to deal with both the stuff that's in the active solution, but I also need to deal with the stuff that's going to be bouncing off the cation exchange sites and potentially what's going to be weathering out of the structure, right? So I really need to know what the size of these reserves are. If it's a well-buffered soil versus a poorly buffered soil, it's going to be a lot easier to change the pH of a weakly buffered soil than it will be a well-buffered soil. Does that make sense? Yeah? Okay. So we need to figure out what this buffering capacity is. We need to be able to deal with the soil's capacity to release or neutralize aluminum protons and the total amount of bases or acids that are needed to bring about that specific shift in pH. The best way to visualize this is something like this, where here's the pH that I want to move to. I want to get up to that pH. My pHs are now at this point. Okay? And basically, how much calcium carbonate, in this scenario, I'm trying to raise the pH, how much calcium carbonate I need to add per amount of soil. Okay? The poorly buffered soil, A, this poorly buffered soil versus the well-buffered soil, the visualization basically says, and tell me if I'm wrong, if this doesn't make sense, but I need to add less calcium carbonate to deal with soil A to bring it up to the pH the desired pH, in this case 6, versus soil B. Now, there's one other piece of information here. You have to understand what your liming agent is as well. It's not just about your soil, but you also want to have an understanding about the strength of your liming agent. Okay, there's lots of different liming agents out there. This is a list. This is from your textbook. I don't expect you guys to be able to see this right now, or be able to read it right now. But there are a lot of different types of liming agents out there with a lot of different strengths. Calcium carbonate is just one type of liming agent. You can have calcium hydroxide. It's twice as powerful as calcium carbonate. Okay? So a calcium carbonate will neutralize 1 proton per 1 calcium carbonate. Calcium hydroxide will neutralize 2. Okay? This is calcium carbonate. This is calcium hydroxide. This guy will neutralize 1 proton. This guy will neutralize 2. So for a 1-for-1 ratio, I'm getting in 2 times my bang for my buck here. Right? Make sense? Okay, how comfortable are we with this at this point, guys? Questions? Okay, well, let's think about one. I got one more slide here, and let's sort of think about this. We'll walk our way through this. Okay, at the high pHs, okay, certainly calcium carbonate will act as a buffering reagent. Okay, at low pHs, we basically throw it in there because we want to raise the pH. Okay, so this is the liming reaction. I'm missing a bracket here. Sorry. There should be a bracket right here. This is the carbonic acid. Okay, now, if we throw calcium carbonate into the soil, an acidic soil, what's going to happen? The proton is going to interact with this calcium. The calcium is going to go into solution. one of the protons is going to be joining onto the calcium carbonate, the carbonate component, and one of them is going to stay in solution. So what have I done? What have I done? What? I've raised the pH by neutralizing one of the protons. Now, if I want to raise it more, I'm going to have to add more calcium carbonate. And that's where this slide comes back into vogue. Basically, it tells you how much calcium carbonate I need to add per kilogram of soil to add it or to raise the pH. Now, you notice that there is no numbers here. How much is that? How much is that number right there? How much is that number right there? Well, that's going to be based on the buffering capacity of the soil that you're trying to raise. Okay? The scenario that we're showing here is two different soils. One's well buffered, one's poorly buffered. But there's going to be a whole spectrum of different types of soils out there, and you basically need to figure out how much I need to raise it to a certain amount. Now, there are basically two ways of doing that. There's a laboratory method, which you guys are going to be learning in the lab. And basically what this is a titration where you take a certain amount of soil and you add a certain amount of calcium carbonate or whatever your buffering reagent is, and you basically watch how far it raises with a certain amount of addition. Does that make sense? Okay, you calculate and you just fit the curve and you can say, okay, well, I have 2 acres and it took this much to raise this beaker full. How much do I need to raise it for my rooting depth? Okay? The other one is basically a rule of thumb, and it works fairly well, but the reality is this is not going to be perfect. The coarser the texture, this makes sense, the coarser the texture, the lower the CEC. So the lower the CEC, forget about the bases, the lower the CEC, one would assume the lesser amount of calcium carbonate I would need to add to raise the pH. Because we're basically assuming a certain amount of base saturation based on the textures. Now that is a poor assumption, but generally your soils will reach an equilibrium in the soil system out in the real world, and this sort of rule of thumb tends to work. Okay? Questions? You cool? All right. Take a look at this sheet. It's in your book. I don't expect you guys to be able to read it right now, but all right. Good?
This has been a production of Cornell University, on the web at cornell.edu.